Hi everybody. Well, I get a lot of questions about transistors and semiconductors in general, how they work. And anytime I do a video on, like I did, the last one I did was on substituting, finding an appropriate substitute transistor online. Some of the folks out there who don't have as much experience with electronics complained because it didn't make sense to them. A lot of what I was talking about was taking into consideration the people who originally were asking this. Already, the reason they want substitute transistors is because they know how to work on this equipment already. They understand how these components work, and they just wanted to hear my opinion on how I go about finding a suitable replacement transistor for one that they can't find anymore, that's no longer in production. A lot of folks came on there thinking they were going to magically learn how to repair electronic gear and know how everything works by that, and were disappointed when the video didn't show that. So I thought I would go back and do a basic video on how a transistor works. I'm going to stick only with bipolar junction transistors for this video, and it's going to be a two-parter. I think before we try to understand how a transistor works, we should first learn how a basic semiconductor works, and there's nothing more basic in a semiconductor than the humble diode. So this part one is going to be how a diode works and what some of the characteristics are and what some of the terminology is. When we finish that, I'm going to do part two, and that's where we'll use the knowledge that we gained from, how a diode works to understand how a transistor works, because really they're very similar, a lot of what's going on. So let's get started. Now right here is a diode. It's a very common diode called a 1N4007. And this one happens to be a cheap one I purchased, I don't know, if eBay or something. It's, one of these cheap foreign-made ones. It doesn't look like an original 1N4007. We're going to check and see if that's exactly, if it works the same later on in the video. But for right now, it is a diode and it does work. What is a semiconductor? A semiconductor is, it sounds corny, but it's something that's partway between a conductor and an insulator. All right. And you might say to yourself, well, isn't this a semiconductor? Because it's not totally an insulator, but it's not totally a conductor. This is a resistor, right? Well, there's some big differences. This piece of wire here is a conductor. And we could even argue, if you had sensitive enough equipment, we could even say that it is also a resistor. Because everything except for superconductors does have a little bit of resistance. Resistance is the opposition to the flow of current. And if you don't know what voltage, current, and resistance is, I highly suggest you stop the video here and you go online and do a little bit of research on Ohm's law, O-H-M, apostrophe S, Ohm's law, and learn about voltage, current, and resistance. There's some very good articles on Wikipedia and on many of the electronics channels out there, and even on YouTube, where people explain this. So learn a little bit about that first, because we're going to use the terms volts, amps, and ohms in these two videos. Now, a resistor, as its name implies, resists the flow of current to a degree. Okay? So, in other words, the higher the amount of ohms that a resistor is rated at, the more difficult it is for a certain voltage to overcome that resistance. And of course, that affects the amount of current that will flow through that resistor. Now, the thing about a resistor, though, is that it generally, and I say generally, does not change with whatever signal you apply across it. The same thing as this piece of wire. So whether I put a high voltage or a low voltage or whatever, put something in line with it, it will still react to whatever's placed across it in the same manner. It never really changes its properties. So it will always have a resistive effect on whatever signal you're putting through it. And it will be a resistive effect of, in this case, 10 ohms. You know, brown is 1, black is 0, and the second black means there's no more 0, so 10 ohms. Again, this is very basic stuff most of you know. And the thing about a resistor is it doesn't really change. Now, of course, some of you electrical engineers out there will say, well, if you heat this up, its resistance will change a little bit. And yes, that's a physical characteristic of different types of materials that are used as resistors. But we're going to ignore that right now. We're going to say this is a resistor and this is a conductor. And this basically has near zero resistance, okay? And this has a set resistance that doesn't change. In a semiconductor, that's different. The polarity at which you apply a current or voltage to this, the temperature of the device, the amount of current and the amount of voltage you apply, all will affect how it reacts to that signal that you're applying to it. Okay, that's the big difference. So these do some very strange things, and it's because of the chemistry of how these things are made up. So let's first take a look at what is a diode made of. Now I think I have some better things to put up on the screen, so I may superimpose that over this. But for right now, so I can kind of guide myself a little bit as I talk, because you know I don't really script a lot of this stuff very much. Here's a diagram of a diode. And you can see there's two main compounds that a diode or a semiconductor is made of. The earlier ones were made of germanium, and the newer ones are made of silicon. And the silicon diodes typically, and silicon semiconductors, are typically more stable and have some properties that are more advantageous than the germanium ones, even though there are some circuits that still benefit from the use of a germanium transistor, or a germanium diode, I should say. And we'll get into that later. It's not as important. But regardless of what it's made of, silicon or germanium, what you see here, these two squares here with the little circles and the dashes, these are the pieces of silicon or germanium. And what they do is, silicon and germanium aren't conductors, aren't very good conductors by themselves. So if you take pure silicon or pure germanium and you try to pass a current through it, it's very hard for it to do so. So what they do is they actually introduce impurities into that silicon or germanium. And the process of putting those impurities in there, and I have a little thing I prepared I'll put up on the screen that you can read. Just pause the video and read it. That's called doping. Yes, from a simpler time, doping the substrate. So by putting, for instance, boron and other chemicals mixed in with the silicon or with the germanium, it causes that germanium or silicon to actually become somewhat of a conductor. And the type of material that they dope it with, its valence number, which that's getting into physics and chemistry, there's trivalent and there's pentavalent dopants. A dopant is the chemical that they use, will cause it to either have a positive charge or a negative charge, or be more susceptible to a positive charge or a negative charge. And I'll put that up on there, which one, the trivalent and the pentavalent. So basically, having two different types of impurities, you can make a positive charge and a negative charge silicon or germanium. And when you fuse those two together, the place where those two things are bonded together is called the junction. Now, a strange thing happens when they put in the junction there, where they combine. You have what's called a depletion region. And that's the area where current cannot flow. So this area right now is trying to stop the electrons on this side from getting to the positive charge on this side. And it needs a little bit of a kick in order for it to do that. Now, in the old germanium diodes, until you put an outside charge of about 300 millivolts or so, and it can be different depending on each device, there will be no current flow through here. These electrons can't get here, and nothing will change. But when you get at about 300 millivolts of charge from here to here, all of a sudden that will allow these electrons to begin to flow, and you'll get the flow of current. Any voltage you apply above that will pass right through there. So essentially, if I apply 1 volt across a germanium diode, I will have about 300 millivolts of that 1 volt will be dropped in this depletion region. Okay, we call that our forward voltage drop. And the rest of that voltage will pass through to the load that it's connected to. So I put 1 volt here, and I connect a resistor from here to ground, right? I will only have about 700 millivolts on this end, and the 300 millivolts will be used up in this depletion region. That's how this thing works. Conversely, if I reverse the leads of my battery or my power supply, and I put the positive voltage here and the negative here, nothing will happen, because I will not increase this negative charge enough to overcome this depletion region, so it will essentially block the flow of current. So a diode will only conduct in one direction. Now there are semiconductors out there that can conduct in both directions, depending on, but we're not going to talk about that in this series. We're only going to talk about diodes and the basic bipolar junction transistor. So that's how this works in a nutshell. I used to love the old experiments we did in science class, where you took some batteries and light bulbs and things, and you showed how current flows and so forth. So I think we're going to do that in this video. So I have 2 C-type batteries. Each battery is 1.5 volts, and since they're in series, they add together. So this is approximately 3 volts coming out of this battery pack. And you can see I have this light bulb here, and I'll pop a schematic up on the screen that you can see, and it will show what the circuit is, so we can get a little introduction to some schematics. And if I put this, I come out of the positive lead and I go into the light bulb, and I come out of the light bulb and I go into the non-striped side of this diode, okay? And you can see that's where the positive goes. That would be the cathode. So I'm feeding my positive lead into the cathode. And then I am going to put the negative lead of the battery onto the anode. And you can see when I do that, the light bulb lights up. You see that? Now if I move this and I just bypass this and put the battery right across the light bulb, you can see the brightness, and the camera is going to adjust for the brightness, but it's actually brighter than it is here. Now let's look at something for a minute. If I back up here, try to get everything in shot and get rid of all the glare of the camera. If I put this on volts, and we're going to measure voltage, and I connect my light bulb, and if I go across this diode, guess what I'm going to read? You can see there's about 800 millivolts going through that being dropped across this diode. And the light bulb has about 2 volts. So you can see we have about a total of about 2.82 volts. So just under 3 volts because these batteries are under load, okay? So that's what happens. And just like we said, we're dropping that voltage there. Now remember, I told you on a germanium diode, you would drop about 300 millivolts. On these diodes, you drop anywhere between 500 and 800 millivolts, but that will change with under different conditions. So let's look at that. Now, if I set my multimeter to this diode check, and see that little symbol there, the arrow with the line over the point? That's called diode mode. And what this does is this takes the battery voltage inside this meter, because this meter has a battery in it, and it applies that voltage across these terminals. So this is your positive and your negative, just kind of like this battery. And it will pass a current at that voltage through whatever it is that we test. And what it will do is it will actually display on our meter here, on our meter display, the amount of voltage drop between these 2 points. So if I put this here and this here, you get a little beep and you can see 559 millivolts. Now, that's strange, isn't it? We just measured when we were running our light bulb, this had 800 and some millivolts, but when I'm using my meter, it's 500 millivolts. Why? Why? That's what we're going to answer in this video. Now, before we do that, let's try something else. Let's take this and let's put it backwards. So now I'm putting the positive onto the cathode, or onto the cathode, and I'm putting the negative onto the anode. So anode, cathode. Take a look. And I hope I didn't say that backwards in the previous clip. If I did, sorry. Tony speaks backwards sometimes because I'm not reading off of a script. I'm going off the top of my really convoluted brain. So look what happens. The bulb doesn't light up. And if we try to measure our volts once again, the full voltage of that battery, 3.197, is dropped across there. Okay? It's not being consumed by this. I'm just reading the battery. So if I take this totally out of circuit and I measure it, it still reads. And that's because I'm just reading the battery. This has no influence on the circuit because it will not conduct in reverse bias. So I just want to show you that. So a diode only conducts current in one direction. Okay, now we put 3 volts and we saw what happened. Now let's put 9 volts. So I'm tripling the amount of voltage going through here. And you can see the bulb gets really bright. Now, do you think we're still going to have that 800 millivolts on there? Let's see. Before my light bulb burns out. I think I'm overdriving it. And you can see it's 843 millivolts. And if I go back to my 3 volts, it's 831. So you can see the voltage drop changes with changes in current through the diode. Now, here's the thing. Let's measure. I'm going to have to hook up some clip leads here. So now let's put some heat on this diode and see what happens to our voltage drop. Hopefully I won't melt my leads. Just a little bit of heat, and look what happened to that voltage drop. And as it cools back down, that voltage drop goes up. So here's the thing. As you put more and more current through this diode, the voltage drop can go up. If you add more and more heat to it, the voltage drop can go down. But that's only to a certain point because they work together with one another. As the voltage drop goes up with more current, this will begin to heat up until eventually, when it gets too warm, it'll start to go down and it can fail. So a silicon diode or a semiconductor does not work like a regular old resistor. And it has these properties to it that we can either use to our advantage or that will be a disadvantage that we have to work around when we're using these types of things. But these are all the kind of things you have to take into consideration. So once again, if we look at the forward voltage drop with lower current, and you can see it changes a little bit with temperature and so forth, but it'll stabilize eventually. And if I go to the higher current, you can see it goes up just a little bit. But that little bit means a lot. Okay? And you can see now I'm putting excessive current through this diode. At first it went up, but now as it's getting hotter and hotter, because I can actually feel the diode getting warm to the touch. And you can see as it starts getting warmer, that voltage drops down till now it's got the same voltage drop as when it had the lower current through it. And that'll keep going down as this thing gets warmer and warmer. Now, the current that's going through this bulb with that 9-volt battery, I measured it, and it's between a half and 3/4 of an amp flowing through that diode. And this diode is only good for a maximum of 1 amp. So the closer you get to that 1 amp, the more you're going to see that temperature thing affecting it. The 3 volts had very low current, and therefore it wasn't making a big temperature change in there, so it was very stable. Okay, I hope that makes sense. One thing I want to bring to your attention is that, if you noticed, it really wasn't the voltage we were putting on this diode that mattered. It was the amount of current flowing through the diode that had the greatest effect on how it worked. Only with one exception, and that is if the voltage I'm putting across this diode is less than its depletion region voltage or a forward voltage drop, then you have a difference, because current won't flow until you get past that forward voltage drop. But after you get through that, it becomes really irrelevant with voltage for the most part. It's all about the current. Okay? Semiconductors are, at least these types, are very current dependent, and they're affected by changes in current. Now here is a basic data sheet on a 1N4007 diode. Okay? And we're going to talk about what some of these things mean. The main things we're going to look at is on the very first page of the data sheet, you have your primary characteristics. Okay? Every data sheet is a little bit different. So, for instance, this is Vishay. They'll do their data sheet a little bit different than perhaps ON Semiconductor or Fairchild or many others. But they're all giving you the same information. They're just putting it on the data sheet in a little bit different organization. They're rearranging the furniture in the living room. Okay? So the first thing they say is IF, and the AV stands for average. So I is current, F is forward. So the forward current meaning when we connect this thing in the right polarity that it's conducting current, is 1 amp. If we exceed 1 amp, what will happen is this diode will not be able to handle the heat and so forth that it will have to dissipate. And it will, in very short order, when you exceed that 1 amp, it will fail to a degree. We'll learn about that here next. Now, when they say 1 amp, notice this diode has 2 leads on it. These metal leads actually act as a heat sink. They can help radiate some of the heat away from the diode and dissipate it. If you cut those leads off, so if you snip these real short and then put it into a circuit board, all of a sudden this maximum volt current will drop a little bit. The bigger the diode, the bigger the leads, the more that's going to be an influence on it. Just remember that. Somewhere they'll tell you that in the data sheet. They usually will say 1 amp. Yeah, see here? Thermal resistance from junction to ambient at 0.375 or 9.5 millimeter lead length. So what they're saying is they want you to have at least 9.5 millimeters or just under 1 centimeter of lead length on each side. If you cut that shorter than that, it will affect that thermal resistance. It's something that they don't always tell you when you learn this stuff. VRRM. That is your voltage reverse repetitive. What does that mean? Well, remember how I just showed you that if we take our power supply and we reverse the leads, we put the positive lead here and the negative lead of our battery here, it won't conduct? Well, it will conduct, but you have to put way more voltage this way than you do this way to get it to conduct. And that backwards voltage, we call that the reverse breakdown voltage. And on a 1N4007, you go to this lower chart, that voltage is 1000 volts. That means that I can put up to a 1000 volt supply backwards on this, and it will do its job as a diode and oppose the flow of current in that backwards direction. But as soon as I hit that 1000 volts, all of a sudden it will break down and it will begin to conduct current, and it will conduct a lot of current and it will fail in pretty short order. Okay, here's a scary little thing. It is a current limited power supply that will measure the forward voltage drop, or measure the voltage drop between these 2 leads, almost like the diode test does on the multimeter. The only difference is instead of putting 3 volts across these leads, it is putting 323 volts. And it is current limited so that you don't overload the circuit you're testing. Now, normally we don't use this for this purpose, but I'm going to show you something. Now here's a poor little tiny diode, and he's only rated for about 80 volts peak reverse. And if I put this in forward bias, so I put this, and I don't want to touch these because there's 300 volts and I don't feel like shocking myself, but you can see there's about 0.7 volts forward voltage, just like you would read with the multimeter. But if I put this thing backwards and I go this way, you can see it's breaking down, and it's saying at about 152 volts it is failing. So at 152 volts, this 80 volt diode is pretty much breaking down and conducting in that backwards direction. Now, if I take this other diode, which is the 1N4001, remember it's good for 1000 volts. And if I connect it in forward bias, once again, you get your 0.7 volt drop. If I go backwards though, nothing. Do you see that? That full 300 volts is there and no current is flowing. But on this one, at 153 volts, we're drawing 1 milliamp. So that's what the reverse breakdown voltage is. Now, some of you who know a little bit about electronics are going to ask me and say, well, Tony, what is a Zener diode? Isn't that what they do? Yes. So what is a Zener diode? A Zener, or Zener diode, Z-E-N-E-R, is a special type of diode that has a different type of dopant on it and has a very heavy dopant in the depletion region. And they're designed to do just what we saw. They're designed to work very reliably in the reverse bias. And they can be set to a specific breakdown voltage. Now these diodes, if I wanted to have a 150 volt or 130 volt Zener diode, and I couldn't just put this in there even though it does that, because this will not work reliably. As soon as you start passing any kind of current through it, it will change dramatically and it will fail. Whereas a Zener diode, or Zener diode, with that extra depletion region that's designed for it, will work very reliably. Now that Zener voltage will vary with current, just like these diodes do in the forward direction, but they are generally stable. Okay, they will work to a degree and can be used as a rudimentary type of voltage regulator because it will shunt everything above that voltage to ground. And they're used in power supplies quite often as voltage regulators, although that temperature change and current and change of voltage drop with current is a negative thing because it's not super accurate. So your regulated power supply is semi-regulated. It will drift a little bit when you use just the Zener diode. Now back to our data sheet. Remember I said this is only good for 1 amp? Well, that's average, and that's what that AV stands for. That means if you, on average, have a generally continuous forward current of 1 amp, this thing will handle it. Although, as you saw, it will get warm and that voltage drop will change. It'll get a little bit unstable the closer you approach that maximum current. But what happens if there's a quick surge? So for instance, I have a stereo. I'm using this diode to rectify the power transformer, the mains transformer, and make the power supply voltage. And I have these great big huge capacitors, and you have this inrush current. Well, for a split second, if it draws 30 amps for 8.3 milliseconds while it pre-charges that capacitor a little bit, the diode will handle it. It won't blow up. But if you put too many capacitors and have too much of a constant current above 30 amps, the diode will fail. So in other words, all you need to remember from this is that the diode can take little short duration surge current many times higher than its continuous current. And that's what this is. VF, that is your forward voltage drop. And look what they're saying here, 1.1 volts. But we measured it with our meter to be 500 millivolts. And when we had it connected to our light bulb, it was dropping 800 millivolts. Where did this 1.1 come from? Well, what you'll find is as you put higher current, this voltage will be higher. So at 1 amp, when you're running it at its full maximum rating, on average, you will see the forward voltage drop go up to about 1.1 volts or 1100 millivolts. That will happen until the diode starts to heat up. As the diode starts to heat up, this will start to drop again. And you saw that effect when I had that light bulb connected on there. All right. Now, what is IR? If you remember, when you connect a power supply in reverse bias, it opposes the flow of current. But every diode will have the tiniest little amount of leakage in reverse bias. And in this one, they're saying it's about 5 microamps or 5 millionths of an amp in reverse. So for most intents and purposes, this isn't going to affect the circuit. In some instances, it will. There are other diodes that have lower leakage than this, and a germanium diode will have much higher leakage than this in reverse. That's one of the downsides of a germanium diode. In addition, the germanium diode will have a lot more rapid change in these forward voltages with current than does a silicon diode. That's one of the problems. That's when they start to heat up and change, they do so very rapidly, and we call that thermal runaway. And it can cause a germanium diode to fail very quickly when you run it at or above its maximum ratings. Now, maximum full load reverse current. Okay, when this diode is running at its maximum current, forward current, and then you suddenly reverse it, instead of 5 microamps, it can leak 30 microamps, is what they're saying, on average. And again, if you test 1,000 of these diodes, this exact model and make of diode, they'll all be just tiny little bits different from one another. So these are average. That's why they're using such round numbers. These are average numbers. You notice this diode here was rated for 80 volts peak reverse voltage, but it actually had a reverse voltage of 130 volts. So it actually exceeded. It was an overachiever. It exceeded its maximum rating. And you'll find that. They're just saying that this is safe to use on a circuit of up to 80 volts, if that makes sense. Rating for fusing, and this is what type of fuse you could use if you wanted to run this so it will protect it from exceeding its maximums. They're saying a 3.7 amp fuse, I believe. Your operating junction storage temperature range. And this is the range that this diode can work within its normal tolerances, is from -50 to positive 150 degrees Celsius. So this can work in a very wide range, but don't let this fool you. If you go between those two extremes and everything in between, it will have very different properties as far as forward voltage drop goes. So it's just something to remember, and the closer you get to these extremes, the closer this is going to get to not working and to actually shorting out. Now, diodes and semiconductors in general also will exhibit a little bit of capacitance. So they act like a capacitor. This junction in here, since you have, an insulator pretty much, the depletion region acts somewhat like an insulator between two electrodes, you will have a little capacitive effect. It's very tiny in most semiconductors, but it's there nonetheless. And it changes with temperature, with forward current, and with frequency. So what they're showing you here is if you apply a 4-volt signal at 1 megahertz frequency, an AC signal, and do the math, okay, for capacitive reactance, it will act like a 15 picofarad capacitor. That's what they're saying here. And if we change these numbers here, this will change. Its effect will change. Very important. Now, in most cases, you can see 1 megahertz, that's really high. That's 1 million cycles per second. And your mains voltage on a mains power supply is either 50 or 60 hertz. Very, very low frequency. So this has no influence, almost very little influence on the circuit at those lower frequencies. But if you're going to pass a high frequency, so this diode would not be good at all for being used in RF circuits, because RF circuits can be in the tens or even hundreds of megahertz, and this will stop working. This influence will begin to rear its ugly head the more you go up in frequency. In addition, there's a certain amount of time that this depletion region needs for it to charge up and break down and allow current to flow. And we call that slew rate. I'm not going to deal with that right now in this video, but just understand it's there. And that timing also becomes an issue. So these diodes are not good for high frequency. And that's where a germanium diode shines. There are specific germanium diodes called point contact diodes and so forth, and they can work at the higher frequencies. But they also are very susceptible to the changes with current and temperature. They have very low voltage, peak reverse voltage. They have very low maximum current ratings. There's all kinds of bad things, but the one good thing they do is they keep being a diode even at very high frequencies. So again, they're used. There's other diodes called Schottky diodes that do the same thing. They have a low forward voltage drop and so forth, but they have different characteristics than a germanium, so they're not always perfectly interchangeable with one another. Again, that's too much to get into in one little simple video, but I'm introducing you to a few terms that hopefully you'll expand your knowledge a little bit about semiconductive diodes. Now I'm just going to show you two charts. This first chart is forward current derating curve. Derating means just that. The maximum rating of this thing for forward current changes with temperature. So you notice if this diode is sitting at about 75 degrees Celsius, which is pretty hot, right? 100 degrees is the boiling point of water, but we're getting there, right? It can still operate at a maximum forward current of 1 amp without failing. But as the temperature gets warmer, and it's pretty rapid drop, when you double the temperature from 75 to 150 degrees C, all of a sudden, this is no longer a diode, it is a conductor, and it will fail. And at 100 degrees C, you can see it's only good for maybe about 650 milliamps, so just over half. And right around here, when we get to about 110 degrees Celsius, this 1 amp diode becomes a half amp diode. And that's what this chart is showing you. If we look over here, they're doing this chart at 60 hertz, so mains voltage. So you're using this as a rectifier in a power supply on a mains powered device. You can see as you increase the number of cycles, so each cycle, there's 60 per second, the longer the duration that you exceed the 1 amp maximum current, the less you can exceed it by. So what they're saying is for one cycle of for 1/60th of a second, I can pass 30 amps through that diode. If I do it 30 amps for 2 cycles, I'll probably overheat the diode and it will fail. At 10 cycles, I now can only have about, what is that, 17 or 18 amps for 10 cycles, or for 10/60ths of a second, or 1/6 of a second. So you can see how that maximum current, you can exceed it only by a certain amount for a certain amount of time. And you can see if you're putting 5 amps through this, this would extend all the way out to here somewhere. It can actually take quite a bit of time at 5 times its rated current before it will fail. But it will heat up very quickly when you do that. And we kind of showed a little bit of the influence of when, current versus heat. So there you go. There's some basic theory on how a diode works. And believe it or not, all those characteristics that affect this diode are going to affect the transistor. But because the transistor is a little more complex how it's put together, those influences work together and against one another, and we'll get into that in the next video. I hope this helps out, and please feel free to add anything or to correct anything I got wrong, and to ask questions. And again, if you ask questions or you make your comments politely, we can work together in this video and learn together. So I hope you enjoyed this. I wish you all peace, joy, happiness, and good health in your lives. And we'll see you next time when we play with way too many meters. And yeah, the guy with the most meters that dies with the most meters wins. Take care, everybody. Bye-bye.